Hello. Did you do the bonus roll?
Yeah, I tried to. I don't know if they're out.
Not really for sure that I'm doing anything, to be very honest.
Oh, you do.
Let's go.
Well, I figured out that when I started, well, I kind of guessed that P, which is the name, which Q is the knife, and E is the name, right? P is name, that's funny. I figured that much.
See, I didn't do that at all. I took each scenario.
Yeah, I just finished all like my people, but I need to go through and like get it ready to.
Yeah.
So, did you find?
I don't know how we did.
No, I did myself in the person.
Did you figure out the 25 with the dipper? 25 with the dipper?
I did.
Huh?
I did calculus.
And 24 with the commas?
Like middle
I didn't
school.
run down.
The method.
Were we supposed to tell what time it was?
Yeah, I think so.
They say
I
that.
thought of it. That's what it said.
So you haven't read that.
Otherwise, state whether the commas was.
And she was like section. It was like a huge paragraph.
I'll go do that.
And I'll show you what I did.
I'm coming to you. I got invalid for both of them. Probably not right.
You did?
Yeah. I got it.
I don't know.
I think I got.
I can read short story or something. Is that
Yeah.
possible?
Yeah.
And does it have to be
You
like
get invalid.
the school level?
Mine's way faster.
Yeah, I thought 24 was
So
valid.
I don't know. I feel like if we have like the concept
We can.
of the full case
Yeah.
study, that's how I set it up.
And how many people did you say?
They had
Does
to-
it, the second one make it false?
Yeah. Even though
Like
you're
where
not.
it's true, false?
I did.
Yeah.
I didn't draw.
Yeah.
I'm gonna do my mom.
Doesn't that make it invalid?
I just said that it says,
Yeah. And that's why I didn't like it. It was funny. One of his answers, he said literally, I don't know. Or this, it was just more explaining it, not therefore. Which he was like,
I
make people to have
I'm pretty sure.
well,
no.
German formulas.
I don't know.
Yeah.
Resources.
I think that difference is like this.
Let us know.
Yeah. And then I don't know if I need, and I put like a little key.
So was this was the reading, and then that was their
Yeah,
response?
the numbers was reading,
Okay.
and then the each different responses, and then I was gonna do like my response underneath each one of those. But I'm not sure if he wants it in that format. Yeah, but he didn't get like a template. Just like that one tiny
No, I haven't
example.
even tried typing into it.
Yeah. So I need to get on Twitter so I can save a picture onto my laptop. Was it the last one? That was last? Oh, okay. No, I didn't do it. Because I didn't know how. Yeah.
No, I was trying to figure
I'm
it
so
out.
glad it was done. I Googled it.
I found it on Slate.
I was going to ask you after stuff.
Yeah, it was. They want to like straighten up. It's a knowledge of no, it was like who's is how it showed. I just wrote it. what she wrote.
I'm not probably gonna take it until, when's the next one? Oh, it's probably not taking it. Still what?
I'm included on my side.
I just how to check it.
Yeah.
You check the time for the premises through, and then
I don't know.
also true, then it's valid.
So they're only valid.
Huh?
Yeah, those are the like.
Cause I think I've gotta take
And
that.
if one is lost, then it's
Yeah, I used highlighting.
I gotta find test centers.
Like this
I know
one.
the county is whatever. I had to take my November. I spent November, right?
I'd rather do it in Y'all are Michael I thought about it. Yeah. You guys saying it, I'm like, I'm not gonna make you do that again. So,
I feel like she kind of liked it.
What did you get?
No.
How much is it?
Actually, Agnes.
She's recording. Wow. He's moving.
I didn't realize that was on. I just didn't
You did not.
He's the added anyway.
Labor registration plus $30.
Nothing's in here.
Phone.
Oh, I'm not in it.
It would be just easier for me to take it.
You're not in it.
Because I can't afford that plus $30.
Maybe I am. Maybe it's so this came in for
I don't think they should.
Oh yes.
But I went to it was free.
Yeah, I think that's how
The
it should.
first one was
Thank you.
the year you're expecting.
You take it in February, but then
Any other time?
Literally,
Okay.
I'm just wrong.
I mean, not that I'm gonna pay a lot, but like I think I can do better.
Where did you get first out there?
I thought that you just go ahead and skip high school and go on fast.
You probably wouldn't get it.
Wait, did you say you could 30?
I did this now.
Is it like, did you say anything? Okay, I thought- I
Yeah.
didn't know if it was just
Okay, so
you.
you can get it.
I just
October 26th.
I just looked it up, and that's what it said.
I literally just like, I read it and was like, okay, that's easy. Or, like,
It confused me. I was like, first of all, what kind of name? So I was like, yeah.
The only reason I knew what it was is because my uncle told me a riddle a couple years ago that was
Where I
pretty
can
much
just give you my driver's license once you go take it.
Hey, you had someone in your family that
Oh, yeah, that one, yeah. Actually, the math professor is also.
Really? Oh, yeah, it's
I don't know if you ever taught this class.
The math one.
Really?
It gave me a headache.
Yeah, the practice.
I can't do that now.
And then I took like the
I
middle
ain't
one.
ready for that.
And that
No,
one,
I'd rather have the paper.
after I got done.
I took it. Do they offer paper and pencils or is it all computer?
They offer paper and
That's why you don't get your.
Okay.
Because I'm gonna read those.
Yeah.
yeah, that's the one I'm retaking. I'm reading for one thing.
The right. Yeah. So then I just
Scroll down.
Yeah. I passed it by this.
Go down to the
You
right.
did that? Yeah. That's exciting though. Yeah. I've taken all of them. Which one did you? It's with middle childhood.
With the program I was in?
Not whenever when you feel like you're classes.
What was it?
I took the math one
I need to get, if I get one more point, I think.
like that, like round it.
That's all I gotta do right now.
Calculus, what do you have to put in
What do you want to do?
Orthopedics and-
So you need that.
That's
or-
true. The calculus on
I
it.
had only taken
So I
one
guess
down for accountable.
Middle childhood, probably wait
Now I've taken all of it.
I didn't feel like it.
I was taking trig and comp together last year.
Color.
Mediums.
Yeah, yeah.
There is.
Taking that one. The
I
one
got a 33 in math, so that was fun.
I'm thinking, winter, as soon as I'm done
My English score was 108.
Fresh. So,
And then my reading score was
take them in a certain my midfield. And I'll take, what's the last one? The social studies one is also very hard. So, I took my two easiest. Oh, yes. How much did I write? Right around 100.
just kind of write paragraphs. They
And then
go over
is
a
it,
situation now and then, but they don't really get hard enough.
It's like the word letters or something like that. If you, when you take it now, they'll be fine.
tell me that?
I'm trying to find other people out there.
I know what it is. I think
You have this book.
because I never did.
It's actually good. Also my dollar.
Is that really your?
That's all I had at first. And then also my next stuff is picnic. No, we just went over the notes and literally write the PowerPoint again. Except this time we printed them off and then put them under. Didn't write on them or anything, just did that and then
Okay.
and we did it like finished. One note is after I don't know. I like writing them down beforehand because especially not from off.
Yeah.
For sure.
Do you want to think about?
Sure. Just write down what page.
At the end of the period.
So when we're going to read that, I don't know which page. I read 50 pages. Easy. Really? Yeah. The whole book? Well, not all of it.
All right, let me check the attendance. Megan, wait.
Here.
Oh,
man. Yeah, I was thinking, I was like,
Elsa. Here. I don't see anybody from that screen. Nobody.
no, they were sick.
Yeah, they. Wait, mark something. Can you see anything there?
Is it possible?
Can you see what I'm writing there? Nothing?
Like, so how do you think? Okay, well, I came in here with nothing, but it's on you. And I have the volume turned up, the microphone's working. It worked just fine last class. I don't know. Oh. Yeah. She's like a snake.
I know this should be about that.
I don't know what she thinks. It's just.
I do not.
So it's like I didn't bring the book.
I mean, it's not.
Correct. Okay. Okay. Yeah. All right. That's good. About students back. We're gonna have a box for students. Probably have to run it through. Yeah. Okay. So I asked her, my boyfriend,
Can I borrow, when you call, I left my phone in my office. Can you call Mike Donnelly, 533-4581. 533-4581. 740.
Boring.
He's usually taking that.
He didn't answer you. Leave a message. Oh yeah, he's coming.
Sorry, operator's sick today.
Oh, that's all right.
And Jane might have filled in.
Okay, let me just
Sorry about that.
that's fine. Let me continue to call the attendance. So, Elsa, did you?
Yes,
Elsa,
here.
yes. Okay. Morgan.
Here.
Allison.
Here.
Katie.
Here.
Jessie. Okay. Leah.
Here.
Catherine.
She's here.
Okay. Madison. Curtis.
Here.
It's working now?
Yeah.
Okay.
On the computer or the document? Okay.
Yes.
Let me see. Go back to the phones.
Today's one.
Document came as well? Oh,
Switch.
power. Takes a second to power up.
Okay. Oh, so the power was off?
Well, unless it was turned off, but it takes a second to. But it's hard to tell when you look at it. The big bright red light looks like it's
Yeah.
on. It's not, but light.
I see.
The other one's better. One is switch. Okay, no, they should see that.
Okay. Thank you.
You need to talk about the password or the. No.
Okay, let's first. I want to just say a few words about the first homework assignment, and well, I have on the feedback section. You should see what problems you did wrong. Because well, I try to explain as much as possible. For some of the questions, a lot of them missed. I would just kind of explain here. So I'm gonna. I think the one many students missed was the last question. Well, for those of you, few of you are gonna have to give you back later. Let's see. The last problem.
All right.
A necessary condition. It says number 48. A necessary condition for this program to be correct. For this computer program to be correct is that not produce error messages during translation. Okay, so a few students missed this question. Necessary condition will be different from sufficient condition. So as we talked about before, a necessary condition is the consequence, not the hypothesis for a conditional statement. So as we know, if you have two statements, a conditional statement, if P then Q. P we call it hypothesis. Q we call it conclusion or consequent conclusion. So whenever you see the word a necessary, flip it. Oh, it's sorry. Okay, so when you see the necessary condition, that means that the necessary condition is the conclusion, not the hypothesis. A sufficient condition is the hypothesis. In this case, which one? We got two statements here. One of them is this computer program is correct. This computer program is correct. That's a statement. And there's another one. It does not produce error messages during translation. So out of these two statements, which one is the conclusion? Which one? That's right, the second one. Because if you look at the keywords, a necessary condition is this, right? So which one is the necessary condition? It's the one, that's the necessary condition, which makes this a conclusion. So that is the conclusion. If that is the conclusion, it tells you this computer is correct. That's the hypothesis. So the correct answer should be if this computer program is correct. If this computer program is correct, then it does not produce error messages during translation. Is correct. A few students had it backwards. Then it does not produce error messages during translation. The other way to write it is to write a contrapositive. You can say if it produces error messages during translation, then this computer program is not correct. Some students did, I think there's one or two students who did that way, and that would still be correct. But the most common way you could do is, as long as you identify the necessary condition as your conclusion, and that would be correct. Okay, there are some other, most of the students actually did it very well. Maybe some students had some trouble with understanding the definition or the truth values. And I think I explained it in the feedback. So if you still have trouble understanding those problems you missed, just talk to me, and email me, and I can help you with those. One thing we can go over one more time is whenever you have a conditional statement, if the hypothesis is false, it doesn't matter what the conclusion is. The conclusion could be true or false. The whole statement, this whole statement, is always going to be true by default. So, because if you don't meet the hypothesis, we're not going to look at the conclusion. You're always going to assume this whole statement is true. So that's one thing. And the other thing is some students, there were two students who did not write out sentences. For those questions, you have to write down, so for all of these questions, contrapositive, inverse, and converse, you must write down in sentences. I did say that in class, and if you just write down the symbols, I did give you some points, but not all the points. And also, pay attention to those keywords, conjunction, disjunction, or, and. When you negate an or statement, it will become and. When you negate an and statement, it will become the or statement. So whenever you have P and Q, when you do negation, you're going to get negation of P or negation of Q. You cannot keep it. You have to flip it. Similarly, if you have an or statement, when you do negation, you get a and. So they have to be flipped. That's something, we call this De Morgan's law, and we verified in class. Again, a very simple example when I say rain and snow. Rain and snow, the negation will be no rain or no snow. You cannot say no rain and no snow. Okay, so that's something I saw in the grading. That's the first week's homework. There's homework due today, section 1.3. Do you have any question about the problems here? 1.3.
24 and 25.
24 and 25?
Yeah.
Huh?
So ones with these people.
So like these two questions, right?
Yes.
Okay. So when you do these, all you have to do is, if it's valid, you would just say it is valid. First thing you gotta do, you use symbols to write the logical form for each argument. And if it's valid, you can verify. Well, it says the rule of inference, right? I didn't really, I don't think I gave you any question that you have to use the rule of inference, did I? If it's invalid, you can state whether it is which error it had. We can look at an example here. 1.3, 22, 24. Let me do one of the questions in the exercise. I can try to do number. If I have something similar to this one, solved then. Okay, so we can go ahead and look at the example I did last time because I think I have something similar to that. One of the examples I did was this one here at the end of the class. If Zach is a cheater, then Zach sits in the back row. That's the first statement. Second statement, Zach sits in the back row. The conclusion, therefore, Zach is a cheater. So if I want to use symbols to describe this, let's try to do that here. So this is what we do. The first sentence, I can call it P. Zach is a cheater. That's P. Zach sits in the back row. Let's call it Q. The first statement will become if P, then Q, right? So the symbols we used, if P, then Q, right? Okay, so you can mark it on your paper. It says my P, statement P, the second one is Q. And then the next part, Zach sits in the back row, which is our Q. You write down Q. Therefore, Zach is a cheater, which is P. Okay, so this is the symbolic form for this logical, this argument. But that's the first thing you got to do. So similarly, when you look at your homework question, you can call this part a P. George solved this problem correctly, and you can call that one. George obtained the answer to as Q. And then so you're going to describe this whole statement, conditional statement in symbols, and this is the statement. So after you identify, change them to symbols, take a look at this logical here argument. We'll see whether it's valid or invalid.
Beautiful.
Okay. So is there a question? So look at format, the conditional statement, Q, therefore P, we talked about 4 special arguments last time. Which one is this one? You can use what you learned in section 1.2. Original statement P, if P then Q. And this argument says what? Because of Q, I got the conclusion P, which means if Q, then P, right? It's equivalent to say if Q happens, then we will get P. So what do we call this? If Q, then P. So that's the original conditional statement. That part of argument, it's like saying if Q, then P. Look at these two. What do we call the second conditional statement? Q, then P. Yes. Somebody said converse, right? Okay. Can everybody see that? That's a converse, yes, from the first week's homework. So if you when you say if Q, then P, you switch hypothesis and conclusion. That's called a converse. And that's the definition you got to memorize. And the converse, is converse always the same or equivalent to the original statement? No, not necessarily true. And we had lots of examples. If I live in Columbus, then I live in Ohio. But when I switch and say, if I live in Ohio, then I live in Columbus. That's not necessarily true, right? So converse, whenever you, this will help you, using converse to help you determine this argument actually is invalid. Okay, and so after that, you don't have to show me that, but you can just look at that, say this is one of the special cases of invalid arguments. This is called so this argument is an invalid argument. You can mark invalid argument. What error does it have? It's the converse error. Because sometimes we think converse is also true and not necessarily true. Okay, so this is what you can do with that. The second one, you kind of have to use the rule of inference. So let me give you an example in the textbook. So we can do exercise number 25. It says this real number is rational, or it is irrational. That's the first statement. Second statement says, oh, this is the same question. Okay, I'm sorry. I should give you a different one. We can do the one here. And I can change it to x is can change it to, so similar example, I can say this number is positive or negative. It's positive or it is negative. That's the first statement. And the second statement, it says this number, this real number, whatever that is, squared, wait, not squared, cubed, maybe, I can make it easier. This real number is not negative. Therefore, this real number is positive. Okay. Well, look at this argument. Is this a valid argument? Well, I have a real number. I'm telling you it's either positive or negative. So it cannot be zero. It cannot be zero. And also, you know something else in the premises. This real number is not negative. So what can you conclude about this real number?
It's positive.
Yes, it's positive, right? And this is a valid argument. It's sort of like a common sense. And we have name for this, because the textbook says identify the rule of inference. I didn't talk about this last time, so if you didn't know that, we call that elimination. So this is called elimination. That's the rule, and it's obvious why we call it elimination. Positive or negative. So positive or negative, and if it's not positive, then it has to be negative because it has to be one of those, right? Okay, so you eliminate positive. That only leaves us a choice of negative. Eliminate negative. It has to be positive. So that's why we call it elimination. The other way is you could, if you don't know this rule, you actually could set up a truth table to verify this is a valid argument. That's a different way to do the problem. Of course, that takes a longer time. But why is the elimination always correct? It's kind of like a common sense, but you can prove it by doing the truth table, which you should have done for, did I ask you to see any of the questions? Yeah, number 6, just like number 6. You could do a truth table to verify this argument is either valid or invalid. Okay, so number 25 should be very similar to the example I have here. Okay, all right, any other question?
For number 38, do we have to do anything besides state what A and B are?
You do have to give me explanations, not just the answer, like why, okay? What your argument is. Say, how did you know? Like, for example, if you say A is a knave, or whatever, A is a knave or knight, so you got to say because of this, 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 and that's why A is a knave, or that's why A is a knight. Okay, I think you have to do something. What we're gonna talk about later, the idea of the argument, and kind of like elimination, a little bit like elimination. You can assume A is a knight, or assume A is a knave, and try to get something that is impossible. Maybe I can, let's see, give you some more. We can take a look at something that some kind of argument that we will use later. Although I did not give you any homework for this, but later in the proof province, we have something called proof by contradiction. That's something you will use. Also, when you do the bonus question, you will use that. A lot of that is just common sense, but I'm going to here to explain it a little bit more. So we have something called contradictions. So, I show you an example here. Where any statement, so we have a statement, P. We know P has 2 possible truth values, either true or false. Okay. Well, suppose I want you to prove this statement P is true, but you cannot, for some reason, you cannot prove it directly. Let's say your bonus question that one you're doing, you want to tell me A is a knight, but how do you explain A is a knight? You could say because A is not a knave, okay? Because any person is either knight or knave, right? If he is not a knave, then he has to be a knight, right? So when you do the question, you could say, okay, let's assume because he's not a knave. And next thing you're gonna do is to explain to me why he's not a knave. Because if he is a knave, something's gonna happen, which does not make sense, okay? And that's why he's a knight. He's not a knave, and then that which way he's a knight. Okay, so the argument is kind of similar to that. So if I want you to prove this statement is true, that's kind of difficult to do that. Well, not very easy. So the approach I'm going to take is assume P is false and see what's going to happen. Okay, so assume P is false. But later, you're not going to try to prove P is false. You're going to try to prove P is true. But by assuming P is false, if you can get a contradiction, that's not going to be possible, right? And then that means P cannot be false. Then that means P has to be true. Okay, so if P is false, suppose P is false, the negation, we do negation of P. Well, when you say P is false, it's like saying the negation of P is true. Okay, so when you try to prove A is, let's say A is a knight, the negation would be if you say that's false, that means the negation is true, right? So A is not a knight, which means A is a knave. Okay, so the negation of P, if the negation of P gives you some kind of contradiction, this C here means contradiction. Therefore, you can say P is true. So that's what it means. I give you another example in real life. Suppose you want to, this is an argument I always in this class and the other statistics class. So if you want to prove that you are innocent to the judge, and one way you could do this, you can say, if I am not innocent, then I will have to be at the crime scene. But I actually was in the classroom with, taking a class. I have alibi for this. So that is a contradiction, because as a person, you cannot be at two different places at the same time, at the crime scene, which is assumed not in the classroom, and at the classroom at the same time. So that is some kind of contradiction. That contradiction tells you you are not guilty, which means you are innocent. So if you want to prove you are innocent, you can assume you are guilty. If you are guilty, you will be at the crime scene. If you are at the crime scene, then you cannot be in the classroom, but you are at the classroom. So at the classroom and at the crime scene, that's a contradiction. Okay. Just like if you are saying, what's a contradiction a lot? Just like common sense contradiction, you are at two different places at the same time. We know that's a lie. Or you can say, I am 40 and I am not 40. That's a contradiction, right? So because you cannot be 40 and not 40. And we can also verify this argument. What does this tell us? If the negation leads to a contradiction, then the original statement has to be true. Okay? We can draw a truth table to verify that quickly here. So to verify this argument is also true. So we start with P and negation of P. So we know P has two possible truth values, either true or false. But if the original statement is true, then negation is false. If the original statement is false, then negation will be true. And we look at the implication, the conditional statement. Now, if the hypothesis, that's the hypothesis, is false, no matter what the conclusion is, we assume it is true. If the hypothesis is true, and then it depends on, I actually missed the column for C. Sorry. Create a column for C. C means contradiction. What do you think a contradiction, the truth value of contradiction is? Say, I am 40 years old, and I am not 40 years old. What do you think about this sentence, the truth value? False. It has to be false, right? So whenever you have a contradiction sentence, give you an example, I am 40 and I am not 40. Well, we know it doesn't matter. So if you call this P, this is negation of P. P and negation of P, it always has to be false, right? Because if I am actually 40, that would be true. But not 40 would be false, because we know true and false will give you a false, right? Okay. So when you have those kind of sentences, we call it a contradiction. But we know any contradiction will always have a false value. Or the other example that I gave you, I am at the crime scene at a certain time, and I am in the classroom at the same time. That would be a contradiction, would be a false. So any contradiction will always have a false value. Always false, never going to be true. And so if the hypothesis is true, the conclusion is false, we know it's going to be false. And so this is the premise. Premises we have, and this is the conclusion. And we know P, copy the value from there, first column TF. So this is a very simple truth table. When you look at this, when is it going to be a valid argument? When you look at the true premises give you true conclusion. Well, that is true. So that tells us it's a valid argument. Okay. But even if you, without the truth table, and just think about it, it makes sense. So if the negation gives us contradiction, therefore the original statement has to be true. Okay. All right, so when you do the bonus question, you can use sort of the same argument here. Assume A is, whatever you want to do, assume A is a knight. See if you can get a contradiction. If you cannot get a contradiction, it tells you your assumption is false, is true. But if you get a contradiction, it tells you the original, the negation will be true. Because one of them has to be true. P or negation of P, one of them has to be true, right? They cannot be both false. So if this is false, if negation of P gives you contradiction, then P is true. If it doesn't give you contradiction, then that might be true. So, and the other one is false. Any other question? No? Okay. So this is something, this kind of argument we will use in the proofs. It's called indirect proof. And when we have trouble proving something directly, we're going to use that indirect proof. Okay, so if there are no questions about homework, okay. All right, so don't forget to turn in the homework to Blackboard, or you can hand it to me and before the end of class today, by midnight. But we're going to skip the application sections 1.4 and 1.5. So 1.4 is more like for electrical engineering, and 1.5 is for computer science majors. So we're going to skip those two application sections. If you're interested, you can read those sections and ask me if you have questions. So we're going to move on to chapter 2. We're going to talk about different types of statements. So far we talked about negation, conjunction, disjunction, and conditional statement. Chapter 2 is talking about something called quantifier statements. And that is also a statement we see a lot in real life and in math and in science, or actually any subject. So what's a quantifier statement? Well, previously we learned a conditional statement. It's like if something, then something, right? Quantifier statement has two types. One of them is called for any, or like English words. Later I would talk about them more. So here just kind of have an introduction. When we say all buses are yellow, that's a quantifier statement. All buses are yellow. It might not be true though, this statement, but it's a quantified statement. And the other type, or sometimes we don't say all. We may say every bus is yellow, but that's the same thing. Every bus is yellow. So all or every, that's the same type of statements in math. We call it, actually we have a name for these. We call it universal statement. Well, it's going to mark it here. Universal statement. The other type of statement we say, well, if I say all buses are yellow, maybe you don't agree with me. You say, well, no, that's not true. There is a white school bus. So you may say, I saw a white school bus. So in other words, you can say there is a white school bus. Or buses, well, let's just make it easier. A white bus. And in this case, there is, or you can say there exists It's a different type of quantified statement. So this is still called a quantifier, but it's a different type. We call it existential statement. As you can see, the difference, universal means it applies to everything, all or every. But existential, it doesn't apply to every single bus. This property, a white bus, only some of them. Maybe 1, maybe 2, maybe 10, maybe 100, but not every single one. So that's a different type of statement. The properties we have, let's say, all even numbers squared. Every even number, if you have an even number, when you square it, you still get even. And that property applies to every single even number. That is a universal statement. If something that is not true for every single one, and that's existential. These are the main two things we're going to talk about in chapter 2. But before that, 2.1, we're going to look at some basic definition in some introduction about these statements. First thing is something called predicate. Section 2.1. Introduction. First thing is predicate. Okay, I think I'm not going to copy down the definition. A predicate is a little different from statement. Statement, it always has a truth value. Say, I am 40. That could be, if I am 40, then it's true. But if I'm not 40, then it's false. So it has a fixed value. Just say Elena is a student. That is true. Well, if I say Elena doesn't have a job, and that would be false. So statement, you already know. Once you are given the statement, you know it's true or false. But predicate, it's also like a sentence. But when you are given the sentence, you don't know whether it's true or false because it has a variable in there. So it's very easy. What's a predicate? It's a sentence with a variable. And whether this sentence is true or false depends on what the variable is. So I'm just going to give you an example to explain that. If I say x squared is greater than x. And this is called a predicate. That's an example of predicate. Because when you look at this statement, I use the symbols, but you could write it in the sentence. The square of any number x is greater than, or a number x is greater than x. So when you look at this, can you tell whether it's true or not? It's true or false? Can you tell? X squared is greater than x?
Yeah, because the x is squared.
Is that when you square a number, do you always get a bigger number?
No.
Not necessarily true, right? For some numbers, it's true. What numbers? Like I think you said it's true. I think you were thinking of like 2, 3, 4, right? Or 2.5. Yes, for those numbers, it is true. But what if x is equal to 1?
And it's equal.
That's equal, right? Or what if x is 1/2? What's 1/2 squared?
4.
1/4. And is 1/4 bigger than 1/2? No, it's actually smaller than 1/2, right? So when you look at this, you cannot really tell whether it's true or false. Sometimes it's true, sometimes it's false. So that's the difference between a predicate and a statement we talked about in chapter 1. Statement, when you look at it, you know it's true or false. But predicate, you will not know whether it's true or false. It really depends on what x is. So that's predicate. Okay, so the first type of question is they want you to find all the x values, the numbers for x, such that this predicate is true. Okay. So let's do how do you do that? I mean, if some of you have a strong background in algebra, there is a way to find out the answer very quickly. I don't know if anybody knows how to solve this inequality. Have you learned this in your algebra class or any other class? Does everybody know? Solve for x. If x squared is greater than x? No? If yes, if you learned this before, go ahead and do that way. Okay, that way is quicker. But what I'm going to do is just like textbook, and we're going to do the slow way. Okay, it's a little tedious, but it will get you the correct answer. And also, we use this to kind of explain the definition of predicate. So this statement here, right here, we are going to call this whole statement P of X. I'm going to use a symbol for that. P is just like the statement we had before, or predicate, the first letter. So I'm going to put parenthesis of X there. This pen line. Okay, so it's, what does this remind you? P of X. In algebra, or calculus. A function, yes, right? In function, if you recall in algebra class, we learned something, usually we use the letter F, or in calculus we use this a lot. It's like a function. Think about it. If I give you f of x equals, let's say, 2x cubed, and they ask you to evaluate, what's f of 1? How do you do that?
Plug 1 in for x?
Yes. Plug it 1 for x, so you get whatever, and you f of negative 3, and you just keep plug it in, and to get answers. So this is very similar to that, but there's a difference. So when you do function, you usually get a number as an answer when you plug in numbers. But when you do a predicate, you don't get a number. You get the whole statement. We'll get a statement. So for example, I'm going to try to work out a P of, I want you to find a P of 2. We want you to find a P of 2, P of 1/2, or P of negative 1/2. So what we do is plug it in. So P of 2, we replace that x, both x's on the left and right. So P of 2, 2 squared is greater than 2. As soon as you plug in a number for x, and it becomes a statement. 2 squared is greater than 2. Is that true or false?
True.
True. But let's plug in 1/2. You're going to get 1/2 squared is greater than 1/2. That would be false. And we can plug in negative 1/2. Negative 1/2 squared is greater than negative 1/2. So when you plug it in, you are going to substitute whatever number for x. And is that true? It's true, right? Because whenever you square this number, a negative number, you get a positive number. A positive number is always greater than a negative. Okay, so we tested a few. Well, but what you need to do, the next type of question is ask you to find what they call a truth set. I guess there is something else before we talk about truth set. It's called domain, and it's very similar to a function in algebra class. Because any predicate always has a variable in there. This variable, just like a function, it has a domain. Does everybody know what a domain means for a function? Yes? Okay. So the domain is like what kind of values x can take. So in this case, we can plug in any number in there, right? Any real number. One of the type of question, if I give you square root of x, suppose we don't talk about imaginary numbers, what kind of numbers we cannot plug in there? That's right, you cannot plug in negative. If you plug in negative, we know if you learn complex numbers, imaginary numbers, you get I, but if we don't allow imaginary, then most of calculators, when you use this, if it's not advanced, they will give you an error message, right? It will just say error, because they cannot do that. So what are the other type of question everybody knows? If a function is 2 over x, what number can I not plug in? It's 0, right? You cannot do 2 divided by 0. And so any number except 0 can be plugged in there. That's called domain. So the domain for this function would be x is not equal to 0, And for that function, is x is greater than or equal to 0. So it's very similar to this, that when we talk about domain of a predicate. But when you look at it here, we don't have a square root, we don't have a fraction, and so we don't have to worry about the bottom being 0. So this is, we can plug in any number. I tested a few. I tested a number greater than 1, a fraction, and between 0 and 1, and between 0 and negative 1. I found some of them are true, some of them false. The next thing is truth set. Which means all the set of elements in the domain that will make the predicate true. Go ahead and put maybe truth set of a predicate P of x is the set of all elements, most of the time numbers, of the domain that make this predicate true. When they are substituted for x. The important things right here, make P of x true. So when you plug in numbers into this predicate, when can you get a true statement? Okay, so go back to this example. We tried a few. We found, well, if the number, if it's 2, it's true. If it's a negative 1/2, it's true. Any other number that will make this true. What about 3? 3.5. Yes, right? Okay. So can you tell me all the numbers that will make this true?
All numbers except for 0 and 1?
Somebody said is except 0 and 1, but 1/2 will not be false, right? So you cannot. You have to exclude those numbers. 1/2 will not be bigger than what?
All numbers greater than 1.
Greater than 1.
And less than 0. And less than 0.
And less than 0. Okay. Yes, that's right. So if you have that observation, great. Okay. What if you cannot see that? Because if you only test 3, might not be that easy for you to tell. So what you can do is you can test more numbers. So from the first one, I kind of tell, okay, it looks like 2 is correct. 1.5, is that correct? Yes. Is 1 correct? No. So it kind of tells me, okay, it looks like all the numbers greater than 1 should work. But as you can see, if you pick a number between 0 and 1, that doesn't work. And I tested negative 1/2, but does it work for negative 1? Any negative number squared, you always get a positive. That should always be greater than negative, right? So that also tells you that is any number less than 0 should be also correct. So you would get greater than 1 or less than 0. So the other... if you have trouble doing this way, you could draw a number line to help you. So we have 0, you put mark 0 there, and usually take 1 or negative 1 as the, because we kind of see 1 doesn't work, and maybe negative 1 will not work, so we don't know, we just mark it there. And you can pick a number from each region. So pick a number from here, greater than 1. We found out it's always true. And we'll pick a number between 0 and 1. I picked a 1/2. You can pick 2/5. And as you can see, when you have a fraction, square it, you always make it smaller. And that's false. And 1 is also false, right? For 1, it's false. For 0, it's false at these two spots. Between negative 1 and 0, it's also false. And negative 1, it's true. Less than negative 1, I picked a fraction. You can pick a negative 2. It's also true. And so we can see which ones are true from here and from there. So you can pick a number from each region. And for those boundary points, boundary numbers, you also have to test them. Between 0 and -1. Oh, yeah, sorry. Wait, yeah, it's true. That's true. So we end up with open greater than 1 or less than 0. Okay. But if you're learning algebra, you can actually solve this. Solve this inequality, x squared greater than x. You subtract the x both sides, and you factor this, and that tells you the two kind of like a critical numbers from calculus 1 to 0. So that tells you all you have to do is pick a number from these three parts, 0 and 1. Pick a number here, pick a number here, pick a number there. You can tell. Okay. If you have learned this way before, you can do that way. If you have not, and you don't want to learn this way, go ahead and just pick numbers. Okay, that will also work. All right, any question?
So is the truth set where you squared that x is greater than 1 or x is less than 0? Is that the truth set?
There's no square. So the truth set, let me write down the answer. So the truth set for this problem, go back, I'm going to put it right here. The truth set is those numbers I find, which is numbers greater than 1. Did you say squared?
Well, because below on that paper with the line graph, yeah, you said those answers, but you just put like a box around it to indicate. That's what I meant by squared.
Yes, that's right. Yes. So usually truth set is a set. So you're gonna put in the set notation.
Okay.
Have you all learned the set notation? In chapter 5, when we talk more about set notation, just looks like this. And if you have an x there, usually you put an x down first and put a line. After the line, you explain what kind of x. Describe what kind of x you have. You put x greater than 1 or x less than 0. So that's how you write it. Yeah, we would like you to put your answer this way. Instead of just write down x greater than 1 or x less than 0. I mean, that technically is correct. But, I mean, to be precise, truth set has to be a set in a set form. Okay, that's any other questions? Now we are going to look at the sum notation, set notation, which we will use in later chapter, this chapter and later, and just for convenience later when we don't have to write down a lot of English words to save time writing. So the set of real numbers, what symbol do we usually use? Does everyone know? R, yes. Okay, the letter R. And the set of integers, what symbol do we use? Z. We use the letter Z. And I guess the reason we didn't use the first letter R is probably because I usually is saved for identity in math. Maybe that's why they didn't choose that. So the set of natural numbers, we use the first letter N. Also, and the whole numbers, I don't think that we're going to talk about whole numbers too often, but just go ahead and put it over here. Use W, first letter. Does anybody know the difference between natural numbers and the whole numbers? Whole numbers includes what? 0. Natural numbers does not include 0. It starts with from 1. So it's like, pretty much if I list it, it's 1, 2, 3, 4, ... And whole numbers starts from zeros and ... Okay, the others I think everybody knows. Well, integers we know you could have plus or minus 1, plus or minus 2, ... I cannot list the real numbers because there's not a pattern. Okay, so any number you can think of is like a real number except the complex numbers. Well, some other notation we use. What if I put a little plus sign right here? What kind of numbers does this represent? Pi Because integer, we know it could be positive or negative, or 0. 0 is not positive nor negative. So z plus means positive ones. Or you can, I can put z minus there. Similarly for R. And N and W, I won't have that because they're always positive, or could be a 0. W, I guess you can have positive. You have R plus or R minus. Okay, and next we can talk about the statements we mentioned at the beginning. The two of them. First we introduce the symbols. The universal quantifier. To replace, in math, we like to use symbols. In algebra, you see that. In high-level math, we also like to do that. So the example I gave you at the beginning, all buses are yellow, or every bus is yellow. For these kind of words, we call them universal statements. We call them quantifier, universal quantifier. When you see that, you can use this symbol to replace it. Upside down A. It means for any or any. Well, I didn't mention that any. You can add any there. If you want to say any bus is yellow, that's still the same thing. But sometimes like all or every, each, or any, it's all like the same thing. Talking about the same thing. Upside down. And the other one is the existential quantifier. And the symbol we use is backwards E. So when you see that, it means there is. I can put an explanation here. So it's like, mostly it's for any. When you see this, you can read it as for any, or every, or I guess all if you want. And this one you can read it as there is or there exists. And another symbol we are going to introduce as belong to or in a set. We're going to introduce this formally in chapter 5, but it's like this symbol. Well, let me just put it belong to. Well, it's like E, but it's around the E. It's not really E, it's round. Okay, when do we use this? I'll say 1 is an integer. Well, let's do -1. -1 is an integer. Example. In English sentence, you say -1 is an integer. Or you can say -1 is in the integer set. So if you want to do that, you could just put something like this. -1 is what belongs to the integer set, which means -1 is an integer. Okay, so that means belong to or in there, in the set. But that's the introduction. Because later, I'm not going to write down the words, because we're just going to use those symbols. It saves a lot of time. All right, my little paper, I don't know. Let me see if they have any paper. Okay, so next thing we're going to do, after we're going to look at some examples to get used to those symbols. All right, the first one we can look at is maybe card number 8, translating from formal to informal. Translating. Okay, let's, because we're going to do both. We're going to translate it from formal to informal and informal to formal. So I'm just going to put translating. Translating words to symbols, or symbols to words. It's like in algebra. So the first example 1, it's on page 80. It says, for any x in R, x greater than or equal to 0. Okay, so this is a formal language. We want you to translate it to informal. This is a formal. You want to translate it to informal. Or you can say English sentence. Okay, how do we say it in English sentence? All real numbers squared is greater than or equal to 0, right? So there are many ways you can say that. The text will actually give you like 5 different answers. So whatever way you like. But the important thing is when you read those formal symbols, you need to be able to understand it. It's easier to write in symbols, but it's not easy to try to understand it. So that's why even if you see symbols in your mind, you should translate it into English sentence. That will help you understand what this is. Okay, so this is pretty much, I'm just going to give you one answer. The square of any, so this symbol here means any, or every. So the square of any, right here, how do we read it? It's a number in the real number set, which means this number is real, a real number. So the square of any real number is greater than, over here it tells us greater than or equal to 0. It's greater than or equal to 0. Well, an easy way to say that is non-negative. If you want to put it non-negative, that also works. Again, it's not, the answer is not unique. You can do any different ways. So when you do the homework, I don't think I gave you that type of question because it's really, you have many different answers. So what we are going to do is to do the other way. So if I give you, on page 81, all triangles have 3 sides. That's informal. We want to change it to formal. What symbols? So all means for any, or upside down A. For any triangle, this triangle has, so let's use you can use a variable to describe it, introduce a variable. So for any triangle, you can use A or T. I'm going to use T, the first letter. For any triangle T has 3 sides. Yes, that's the symbol. If it has 3 sides, we don't really have any symbols for that. We just have to keep the words in there. The next one, no dogs have wings. Okay. So negation, how do we say that? No dogs have wings. We want you to use the symbol.
Upside down A. Yeah.
For any
Dogs.
with dogs, for dog A, for D. But what about the dog D?
Have wings. D.
Have wings?
D has
No.
wings.
D has wings? No dogs. No dogs
Oh.
have wings.
Oh. D doesn't have wings.
Yes, D does not have wings. So we want the format is always for any something, for any triangle or any dot, you use a variable there to make it easier for you to write down the next statement. Whatever property about this dot or this triangle either has or does not have. Next one, some programs are structured. Some programs are structured. Okay. Change it to symbols.
Backwards E.
Yes. There exists a program, and we can again use the first letter of P. What about this program P?
P is structured.
Yes. Usually whenever there exists existential statement, we add the word such that. Let me use such that. So later I'll probably just write down ST. Such that P is structured. Okay. So that's the format. There exists, you write down there exists something such that there's a property about that. Now next we're gonna put, so far we talked about universal and existential. So next we're gonna include conditional statement in here from chapter 1. We call it universal. We still have to do translation, but now let's go ahead and look at it. Just example 3 on page 82. The first question says, if a real number is an integer, then it is a rational number. But this time, as you can see, we have if then in there. And also, a real number means any real number. So universal statement in there. Okay. How do we rewrite this in symbols? For any real number, x, for any real number x, we can use symbols. So let's use x for this real number. For any real number x. Now what's the property about this real number, the statement? What about it? What about x?
It is an integer.
If x is an integer, I can also use symbols. If x is an integer, then what? X is a rational number. Oh, by the way, I forgot to introduce the rational number. Maybe you can add one more back there. We use the letter Q for a rational number. Okay, so go back there, add one. The set of rational numbers. We use the letter Q for that. The reason.
Sorry, I have a question. For irrational numbers, would it be the negation of Q? Or is that different?
Wait, say it again?
For the notation for irrational numbers, would that be the negation of Q, or is that just a different notation?
I don't think we have a notation for irrational number, or you can call it radical number. We don't have a symbol for that. And
I was just curious.
Yeah, we cannot. You're asking if we can use negation for that. We actually cannot use negation because negation is for statements. Q, these are sets.
Oh, okay.
Sets. The idea is kind of similar, but not exactly the same thing. So it's like a rational number. What you could do is to do this. Well, we haven't talked about this, but it's a good question. In chapter 5, when we'll talk about that, you could do R minus Q. R is all real numbers. Q is rational, because if you take away rational from real numbers, you get irrational. So that's one way you could do. But just a side note. Okay, so Q means rational. A good way, a tip for you to help you remember, because rational numbers usually, what kind of numbers are rational numbers? Like most fractions. Rational numbers are the same as fractions. A fraction usually looks like a quotient, right? Okay, so maybe that can help you to remember Q, quotient. So the easy way. All right, so that's how we rewrite this. Any other question? Okay. Maybe I should go and stop here. So let me double check. Is Jessie here?
Yeah.
Yes? Okay. And Madison, is Madison here?
Yep, I'm here.
Okay, all right. I think we can finish it here for today. Got 2 minutes left. Well, let's just stop here for today.
Is homework 2.1 due Wednesday?
No, next week. Next Monday.
Oh, okay.
I think so, yeah.
Yeah, do you for this class?
Yeah.
Your meeting has ended.